Hello folks, in this video tutorial I will be taking apart and analyzing it in the 3D Experience platform, and this part is subjected to a creep loading. So let me remind you that the native solver in the 3D Experience is actually the Abacus program, and in some of the tutorials I take people which are the work of people which are directly done in the Abacus CAE and go through the step, replicate the process to show the interested individuals what the sequence is in the 3D experience and how the interface differs from the Abacus CAE, and it's substantial. This particular video tutorial was based not on the work of on the work previously done in Abacus CAE, but it's done in ANSYS. So let me show you first of all what the geometry is. The geometry is shown here, and it's taken by the reference of this professor down below, and it was done in the ANSYS program. Okay, now the left well this is a sample, a uniaxial sample test. The part, of course, is made of an adhesive epoxy adhesive, and therefore it's very amenable to the creep phenomena. However, what I'm going to be doing is taking only 1/8 of this. So using symmetry, I will be modeling in 3D, but only 1/8 of it. And the work of this YouTuber was actually done with ANSYS using the plane stress. However, we don't have plane stress elements or we don't have any two-dimensional elements except for axisymmetric in 3D experience, and therefore I will be doing it uh, uh, in 3D. Okay. The actual data from the work of that professor, which I showed you the reference to, comes from his paper, which is over there, in case you're interested in. Now, in ANSYS, there are several models. There are 13 or 11 models which are uh, related to creep. Now, he is using the second one, which is time hardening. And the values that he's using for this relationship that you see down below are taken and recorded in that table up there. The problem is that in the Abacus program, the numbers are going to be, some of them are going to be different because the model is not written the way it is. And I'm going to go through it. First of all, try to find out what the equivalent numbers are. And then once we know that, then we can go and model it in the 3D experience slash Abacus. Okay, so on the left side, oh, this particular slide is taken from the work down below of somebody else down below, which is actually a very good site, and it discusses same issues in the Abacus program. But anyway, the corresponding time power model on the left side in the Abacus program is written as you see here, and the one in ANSYS that is used by the previous reference is on the right hand side. The question is, how are these related? So first of all, you look at the powers. N and C2 are the powers of the stress, if Q is the effective stress, and so that's obvious. The same thing with M, T to the M here and T to the C3. Obviously, this M is going to be your C3. As far as C4 is concerned, the value 0 is used by the YouTuber, and that's because there's no temperature effect anyway. So this does not appear here. If C4 is 0, this does not appear here, which is precisely what I've got on the left-hand side in the Abacus model. Now, Q naught is something for convenience. I'm going to take it to be 1, okay? Now, if you take Q naught to be 1, and you equate whatever is multiplied by this thing and whatever is multiplied by the terms on the right side, you will get the relationship between C1 and epsilon 0 dot. So either you write it like that, or you solve for the epsilon 0 creep, and you get it in that form. Remember, this is what the 3D experience slash Abacus wants. So the C1 is used by the YouTuber from his paper was given in the previous page, and therefore we have to get this value accordingly. So this is the stuff from the ANSYS calculations. So if you plug in the given values based on the information that was given to you, you get the value dot creep. Okay, actually this should be not. Okay, so this should be not. Let me fix that thing, because if you look at there, you see that yeah, it's this value. This is not correct. That should be E0. Okay, that takes care of this. And then we go here, and that should be 0. I'm sorry for this, but let's move on. Okay, so what we need in Abacus is that number, Abacus / 3D Experience. N is the same as C2, M is the same as C1, and of course there's no temperature effect, and therefore this is 0. And there's no temperature effect, yeah. So the material that's used, we have to specify its Young's modulus and Poisson ratio, and based on the information provided in that paper and that ANSYS work, ANSYS implementation of that work is 2,232 megapascal, Poisson ratio is 0.4, and then we go to the creep. Okay, we go to the creep, we have to specify, and this is the kind of thing that you have to put in the 3D Experiences page. So Q naught, I conveniently take it to be 1 MPa, N and M were calculated. I mean, basically based on the previous YouTube channel, and then epsilon 0 we just calculated, came out to be this. Okay, so this is how the conversion goes between the work in ANSYS by the gentleman that I referred to, and the work in 3D Experience / Abacus that I'm going to be showing you. I will be using a three-dimensional element because there are no two-dimensional elements in 3D Experience, and one layer of elements through the thickness. Notice that at the right-hand side, I'm going to put a 4 megapascal pressure, and these are symmetry planes that you see here. So as far as running is concerned, I'm going to do it in 2 steps. The first step is a static step, which means basically things are going to get loaded immediately, stresses will develop, etc., etc. And these are the numbers that I'm going to be using. So this is a step duration. This is not a time-dependent problem. The first step is actually just straightforward static, except this is dummy time. And the second step is a quasi-static step. Quasi-static step where the total duration is 1,000 seconds, and these are the increments that I'm going to be using. I'm going to include large deformation in both of them, and there is a checkbox here. It says use explicit integration for creep behavior. This saves time, but in the simple problem that we're doing, it really doesn't matter whether you check it or not. You pretty much get where you want to go. Notice that I can plot the deformation displacement at the very right hand side of the sample where the load is applied as a function of time. And you can see that as time goes on after 1,000 seconds, that deformation goes from, this value, these are in meters, by the way. So it goes from roughly 0.18, something like that, millimeter to 1 point something, 1.6 millimeter, I believe. But anyway, it shows you the concept of creep. Okay, and if you look at the displacement, the von Mises stress, this is at the beginning before the creep takes over. This is the von Mises stress distribution in the part, and this is after 1,000 seconds. There's some differences, as you can see. Obviously, things will change. Okay, so let me go ahead and do the thing in 3D Experience. Okay, to it and make that two-dimensional cross section and then pad it. Okay, so on that vertical plane, I will sketch. I will draw this line here, 65 millimeters, just so that I have some reference for things that I'm drawing. So let me do a line here from there to there and 65 millimeter. Okay, so let's make this thing 65. And then the rest is going to be easy to do. 65. Okay, good. And now we do the rest of the profile. So from here up, this is going to be 10 millimeter in a minute. I'll dimension it later on. And then to the right, because with some dimensions, this is 10. And this is 20, I believe, 24. Okay, so 24. Okay, good. And then let's do it on the other side. So 5 millimeter up and 26 to the right. Okay, let's do that. So this is going to be 26. And this one is going to be 5. Okay, and now we're going to do the arc. So there are different ways of doing it. So here's what I'm going to do. I'm going to go up here. It's going to be the center, come down to that point, and then go over there. Okay, so that radius should be 25. 25, make it 25. Okay, good. So we got the things worked up. Exit. And then we're going to pad it. So we go to model, pad it by 2 millimeters. Taking a 2 millimeter thickness. Remember, the whole thing is, well, actually 1 millimeter because the whole thing is 2 millimeter. So 1 millimeter thickness because we're taking 1/8 of the model. All right, that takes care of this. Now we're going to do the material. So under tools, create a material. Create a material. I'm going to call this thing epoxy adhesive. Epoxy adhesive. And it is November 13, 2023. All right. All right, it's going to create it. Now we have to, of course, input the data. See if we can find it. Let me refresh this. Epoxy adhesive right there. Apply. I'm going to close that. Apply it to that part. Green check mark. Okay. So double click. And this is where we're going to put our stuff. So structural, we don't need the density because this is a static problem. So abacus multiphysics, mechanical, elasticity, elastic, and it was 2000. Let me see now. If you look at the slide, 2232, 2232 MPa, Poisson ratio 0.4. Okay, and then we go to viscoelasticity, creep and swelling. We creep. Okay, creep. There I go. Creep. You click on it, and we will use the power law right there. So what goes in there is going to be this number. Okay. So all right. So back to 3D experience. So this is going to be 1. That's going to be 2.87. These are exponents, don't have any units, so minus 0.427. And then this is the one that we calculated through that formula, which incidentally I made a mistake in the subscript, but the value eventually got fixed. 3.987 e to the minus 11. Okay, that's good. Nothing else. Let me say okay. All right. So now we can go and do the meshing. So we change applications, structural model creation, empty FEA model, because we will do the meshing ourselves. We don't want anything automatic. Okay, so if you click on the mesh, and there is the sweep mesh, sweep 3D mesh, you select that. It's going to be sweeping it from one end to the other end. Number of layer is 1 and the value is 0.7. That's what I suggested. Okay, and then we say mesh. There we are. Okay, let's do the 3D properties. Properties, here is the solid section. You select that. The material, correct material will be picked there. Epoxy adhesive, November 13. Excellent. So we have meshed it and we have actually done the 3D properties. Now we're going to go to, because we're solving this thing as a standard problem, not explicit, so we can do it here. Okay. You can also do it at the mechanical scenario creation because you have access to both implicit here and there, but I'll go to structural scenario creation. Now, I can create the first step, run it through, look at the results. That's the static case. And then once I'm happy, go and do the quasi-static one and then run it. Or I can do them at the same time and then, of course, look at the result at the same time. That's what I'm going to do. So structural, the finite model that we created. So there's going to be two steps. One of them is static and the other one is going to be quasi-static. So let's see now. Notice that there is a red exclamation mark here, no procedures. So we go to procedures tab, and then the first one is a static step. This number is entirely dummy. So remember I suggested that we use a very small number. It really doesn't matter. Uh, uh, 1 e to the minus, this is just dummy time, 1 e to the minus 6. And then for all of these, I use 1 e to the minus 7. So let's go here. 1 e to the minus 6. And then this is going to be 1 e to the minus 7. These are totally at your discretion. 1 e to the minus 7 and 1 e to the minus 7. In fact, yeah, I could have done it as okay. If you go here under advanced, include the geometric nonlinearity. That's what I'm going to do. Now, if you uncheck that, you could have done this thing in just one step, okay? But that's how I'm going to do that. So we say okay. All right, let's go and apply our boundary conditions. So we go to boundary conditions. There is something called the symmetry boundary condition. It's just like a roller symmetry, planar symmetry. So we select that entire face. You're going to put it on a roller. We can do this or we can do the back. It really doesn't matter because in my slide here, seems that I have done the front. I'm going to do that exact same thing here. It really doesn't matter. Okay, so we go here, and you have to do this thing separately. So another one for this side, you cannot do them at the same time. Okay, and another one for the bottom. Now the bottom is probably made of three surfaces, so it may not be. Oh yeah, no, it's okay. That's good. Very good. Okay, so that takes care of the uh, symmetry. Now we're going to apply pressure, load, pressure on that face. On that face, value is -4 because I want it to be tensile. That's why I put a minus, and then right there, -4 MPa. Good. And so that takes care of the first step, which is the static step, right there, right there. And then we insert another one. Procedure, we do a quasi-static one. Total 1,000 second. And these numbers, I gave you some suggestions here, and they were picked based on the value of that reference. So really doesn't matter. We could have done it our own way. 1, 0, 0, 1, and 5. Okay, so let's go back here. 1 second. Oh, yeah, so this is going to be 5. It looks like let me see for a second. Yeah, so I took the default. All right, good. So let's go back here. Now, notice that under advanced, this is already checked because in the previous step, I already checked this, so it just goes through. Okay. Now, one thing I want to show you, and that is, let me update first of all. Okay, so I guess I have to, something that I forgot to do, and we go here. Yeah, so we go back there, and for this value, I put down 0.01. You have to specify that. So I tried 0.1, 0.1. Okay, so 0.1, and we say okay. Now update. There shouldn't be any errors. Very good. Now, one thing I want to point out to you: if you go to this, if you go here in this pull-up menu, Feature Manager, notice that there's two steps. Step one is static. Step two, or uh, step one is static, and then followed by the quasi-static one. Okay? And all the information is propagated. All the boundary conditions are propagated here. In the event that you wanted to something not to be propagated, you just go ahead and deactivate it. But that's not the case. This is fine. We want that. The one last thing we want to do is we want the time history data at this node, at this point. Okay, that's the end of the uh, at, at the end of the part. You can do it at this node or that node. It doesn't matter. So I'm going to request that under results. Uh, Sorry, not there. Let's go ahead and do that. Now the simulate tab, under output, uh, field history, not time history output. I want this point and I want displacement. Just the translation is good because we don't have rotational degrees of freedom here anyways. So we have actually requested the output like you see here. Okay. And then we say, okay, let's do a quick save. I don't think I forgot anything. Find out. By the way, these are all linear elements. We can check linear element and reduce integration. If not, we're going to change it. Let's actually go ahead and find out. Under the element type assignment, so you can see better, double click on global element type. Oh, it's not reduced, so let's change it to reduced. Okay. And this one you don't have a choice, but for the break element you use reduce integration. So what I have here is actually this. All right. Say okay. We do another save. And then let's go ahead and simulation. Let's do a model check, quick model check. I don't anticipate any problem. Let's do a quick simulation check. and finally simulate, which is actually the running process. It's going to be very fast. And by the way, that large deformation that I activated, even if you deactivate it with nonlinear geometry, the results are not going to be much different. I didn't try it, but okay, so almost done. Good. And finally, we're going to simulate, which means actually you submit the job. And now it's going to be running. Once you say OK, and this thing pops up, it's going to be running. Click on the iteration. That's basically your monitor tab in the Abacus CAE. All right. So notice that this is supposed to go to 1,000 seconds. It's getting there, 33%, etc. Almost done. Good. Extracting results. So let's plot the von Mises stress at the end of the static case. Excuse me. I'm still recovering from this cold. All right. So what we have here is a static case, okay? And look at, for example, at the very end, you're gonna have your stress, von Mises stress distribution right there, okay? If you want to look at your displacement, select the displacement. And I think I told you it was 0.182. This end displaces by 0.182. Now, when the creeps start, you change this to quasi-static step. The very first one is what we inherited from the static step. As far as, let's change it to von Mises stress. Okay, this is what we had. This is what we had from static step. And now, as the creep is taking place, you go all the way, these values change, and at the very end, this is what you get. If you look at the displacement, remember it was 0.18, right? 0.18 millimeter. If you look at the displacement, now it is 1.8 millimeter or 1.7 millimeter. Okay, good. So that takes care of this. Now, what if you wanted to plot the displacement of that node as a function of time? Remember, we requested that. So we go here to the XY plot from history, and I want the displacement, this translation that I requested, the magnitude, which is going to be pretty much the same as whatever is in the X direction, and output 3 that I requested. And I say, okay, that's going to give you the displacement of that point that I selected as a function of time in units of meters, of course. There, okay, which is your, basically at the end, it's going to be 1.8 millimeter. These are Khabbaz's ANSYS work, and now he didn't do any mesh conversion study, I didn't do any mesh conversion study, but they are very much in the same ballpark, and they're very close to each other, actually. All right, good luck.